Okay, so the next topic is called bagging, or bootstrap aggregation, which is a way of using trees in an ensemble, an average of trees, to improve their prediction error. And as we'll see, that the bagging methods, well, I'll mention the bagging method is due to Leo Breiman, and it's kind of a bootstrap process. And I remember seeing, when the first time I saw this, when would that have been, maybe in the mid-90s? I knew a lot about the bootstrap. Actually, I was a student of Brad Efron, who invented the bootstrap, and Brad and I wrote a book together on the bootstrap in the early 90s. And then when I saw the bag idea from Leo, I thought, this looks really crazy. Usually the bootstrap is used to get an idea of standard errors or bias, but Leo wants to use bootstrap to produce a whole bunch of trees and to average them, which sounded really crazy to me. And it was a reminder to me that when you see an idea that looks really crazy, it's got a reasonable chance of actually being really good, right? If things look very familiar, they're not likely to be big steps forward. This was a big step forward, and it took me and others a long time to realize that.
And bagging, and you'll see random forests that we're going to talk about as well, they're used all over. And I just was at a talk the other day where random forest was the primary tool used in a big image classification problem, using state-of-the-art methods, and random forest was at the heart of it.
Okay, so let's see what the bagging idea is. So it's the basic. It's a way of taking a bunch of independent observations and taking their average to reduce variance. So just recall, if we had a bunch of observations, Z1 through Zn, the independent observations with variance sigma squared, that if we take their average, the variance of the mean y bar is sigma squared over n. So by taking an average of independent things, we reduce the variance by n. That's good. So what does that say to us in terms of supervised learning? It says if we had more than one training set, we could grow, for example, a tree on each training set and take the average tree, right? Now, that doesn't really help us, probably, because we don't have multiple training sets. Let's assume we just have our the one available training set. Well, bagging is going to try to achieve this now by taking, not without new training sets, by taking bootstrap samples to create sort of pseudo-training sets. Grow a tree on each one and then take their average. That's the simple, but I think very clever idea of bagging. So we're going to take bootstrap samples from a training set of the same size as our original sample. That's the usual bootstrap. And I can maybe draw a little picture here, just so we can think about it. Here's our original training set. We're going to draw bootstrap samples. Again, they're samples taken with replacement of the same size from the original data set. And we'll take lots of them, maybe a few hundred. Okay? And for each one, we're going to grow a tree using, for example, the procedure we just went over. On each of these training sets, we're going to get a little tree. Okay?
Actually, quite big trees.
Big trees, that's right. I said little tree, but actually, in fact, turns out we don't need to worry about pruning the trees. We can grow large trees and just, when we average them, we'll reduce variance. We don't need to prune even. That's another happy coincidence. So, notational-wise, we'll call the tree that we grow on the Bth tree, again, B going from maybe 1 to 200, f hat star B of x. So, the prediction at feature x for the Bth tree we'll call f hat star B of x. Our overall bagged estimate prediction is just the average. So in other words, we grow these trees, we have a new x, and we want to predict at x. We ask each tree, what's your prediction for x? And that's f hat star B of x, and we average the predictions, and that's called bagging.
It's a really clever idea. So, you know, the old idea of pruning a tree back was to reduce the variance, you pruned it back. But when you prune it back, you give it a lot of bias because you make it necessarily just a much coarser tree. So Breiman's idea was, don't prune back, have bushy trees, which tend to have low bias, and get rid of the variance by doing this averaging.
Right, and we can apply this to regression or classification. Here I've basically implicitly assumed we're doing regression so that the prediction is actually a quantitative variable. But if we're doing classification, we can just do a majority vote. So we can have 200 trees. Since we have two classes, we make a prediction at each x, and we ask each tree, what's your class prediction? And suppose of the 200, 150 say class 1, and the other 50 say class 2, then our prediction is class 1. So we can just take a majority vote among the B trees that we grow. Okay. So here's actually the heart data. This is the result of bagging the heart data. So along the horizontal axis is the number of trees, which we grew up to 300 trees in this case. And what do we see here? Well, we have We have the test error of bagging, first of all. Remember, we had a test set we set aside. And it's the black curve. And its error is around a little over 0.25. If we go over the left here, we'll see actually the result of a single tree. So in this case, bagging improved a single tree, maybe just by 1% error.
Actually, the dotted line is a single tree, right?
Okay, thank you. So the dotted line is a single tree. So it looks like we may have improved the prediction error by perhaps 1%. Not a great win in this one case. The random forest, which I'll talk about in a few slides, is a sort of it's a more advanced form of bagging where we do another trick of Bryman's that's going to improve things here by maybe another couple percent.
So in this figure, we've also got two error curves called out of bag, for both for bag-in and random forest. We'll describe it for bag-in now. So the out of bag error is a very important part of bag-in and random forest. And it turns out it's a essentially free way of computing leave one out cross-validation. And it works as follows. Each of the bootstrap samples includes about 2/3 of the observations, and about 1/3 of the observations are left out. And of course, for each bootstrap sample, a different 1/3 is left out. So suppose we want to compute the error for a particular observation. Well, we can take all the bootstrap samples that didn't include that observation, and we just average their predictions for that observation and use them to predict that observation. Well, that's going to be, that observation wouldn't have been in any of those training samples, and so that's a left out error estimate. And so you can just accumulate those predictions in that fashion for each of the observations, and that's called the out-of-bag error. And if you think about it carefully, if B is large, the number of trees is large, that's essentially leave one out cross-validation, and it just comes for free. And so that's what was given in this slide here. So for bag-in, that's the green curve, and it's quite a bit lower than the black curve above, which is the error on the test set, the green curve. And of course, there's variability in these because these are just samples of numbers, and so that variability is just due to the division of the test samples and the training samples. Okay,
so the next idea that Leo Bryman had a few years after bagging was called random forest. And the idea here is that we're taking an average, and an average would be lower if the things being averaged have lower correlation. So the idea of random forest is to build trees in such a way as to actually make the correlation between trees smaller.
Even smaller than you get from bootstrapping.
Exactly, right. And again, this is one of these ideas which, when I first saw it at least, looked really bizarre, but it's a very clever thing. So what is that idea? Well, the idea is we're going to do bagging exactly the way we did before, except with one change. When we build the trees and we make splits, every time we consider a split in a tree, we don't consider all possible predictors, as we normally do with trees, but rather we select at random m predictors among the p. And the m is, say, typically about the square root of p. So in other words, if there's 100 predictors in our data set, every time we go to make a split, we don't consider all 100, but rather we take a random subset of 10 of them. And the other 90 not even considered. Only the 10 are even allowed to be considered for the splits. And the random selection is made, a new selection is made at every possible split. Okay, so again, it seems kind of crazy to throw away most of the predictors at every split. But the effect of doing this is that it forces the trees to use different predictors to split at different times. And since we're going to build lots of trees, although if a good predictor is left out at a given split, it's going to have lots of chances in that tree or in other trees to make an appearance. So although it seems crazy to throw away, in a sense, most of your predictors at every stage, since we're going to build a large number of trees and then take the average, it actually works out very well.
So even with the same training sample, if you grow two trees, you'll get two different trees because by chance it'll pick different variables each time.
Okay, so let's see how random forest does in the hard data. So remember the bagging error, test error was about here, and random forest improves by maybe 1 or 2%. So again, by doing this trick of throwing away predictors, we've decorrelated the trees, and the resulting average seems to do a little better. And the out-of-bag estimate is also a little better than it was for bagging. Our next example is a high-dimensional example from Chapter 8 on gene expression. So this is using the gene expression from 349 patients. These are cancer patients. The gene expression of 4,718 genes to predict their cancer class. And this is a common activity among people in statistics and genomics to try to do classification into things like cancer class based on the gene expression of genes in cells. So in this case, there's actually 15 classes. The one class is healthy or normal, and there's 14 different types of cancer. So we're going to apply the random forest method we just described to this high-dimensional data. But instead of using the entire set of 4,718 genes, we're actually going to pre-screen the genes. We're going to choose the genes having the highest variance across the training set. And it kind of makes sense if we want to reduce the number of genes to use variance, because if something has small variance across the training set, it's probably not very predictive, right? So choosing the ones that have the largest variance are the ones that are most likely to be predictive.
So is that cheating, Rob? You went from 4,700 genes down to 500 genes?
That's a good question. Is it cheating? Is it biasing things? Well, it's not, because the outcome, the class, is not being used to choose the genes. It would have been a problem if we chose the genes that vary the most from one class to another. In other words, if we use the class label to choose the genes. But because we're just doing this just looking at the overall variance, without regard to the class label, this is fine. It's not going to bias our results.
So it's unsupervised screening.
Exactly. So supervised screening creates a bias in our would create a bias in our cross-validation or the out-of-bag estimates. But if we do it unsupervised, it's no problem. That's what we're doing here. So again, for comparison purposes, we divided the data into a training and a test set. We're going to apply random forest to the training set, and for 3 different values of the m, which is the number of variables that we choose at each split. The random number among which we're going to choose at each split. So let's see the results. So again, a horizontal axis has the number of trees, total number of trees. We go up to about 500. On the left, we have the single tree results. So remember, we've been saying quite often that the trees are attractive because they're interpretable, but they really don't often predict well. And here we see a case where they're predicting pretty badly. Here's the single tree, and its error is upwards of 50 or 60%. Now remember, there's 15 classes, so an error of 60 or 70% isn't crazy, right? Because there's so many classes, but it's still not very good.
It's interesting, Rob, how quickly the error comes down with random forests, and then sort of levels off. It doesn't take long before, by about 100 trees, it's kind of leveled off and not really changing that much.
Exactly. And that levels around, so we look at, looks like the best is around, well, if we use m equals p, which is just bagging, right? That means that at every split we're using all possible predictors, or considering all possible predictors. That's bagging. Those are usual trees. That gives us the gold curve. Random forest, the green one, with the square root of p. So that's where we're throwing away, we're retaining square root p and throwing the rest away. You see, it gives us an improvement of perhaps 3 or 4% over bagging.
One nice thing about random forest and bagging is that you can't overfit by putting in too many trees. The only benefit of adding more trees is it brings the variance down more, but that at some point the variance just stops decreasing, and adding more trees doesn't help you at all, but it never will hurt you. So by looking at, for example, these out-of-bag errors, you can just decide when you've done enough.